And today, Tom, is going to be really good because what we're doing is we're not so much doing calculus techniques, rather we're going to be looking at graphs of functions and their derivatives and their second derivatives and trying to recognize relationships. So that's going to really inform our visual understanding of how they're related to one another. So we will start off nice and slowly, all right? We're presented with this function here, and it says graph the first derivative and the second derivative. So draw a graph. Well, what we know, if this is the function, okay, what we can see from it is we can see when it's decreasing and when it's increasing. And so that point there, I'm going to say that's about halfway between the two. Some of them will require a little bit of an approximation, a little bit of a guess, all right? But right there we can see the minimum occurs there, which means f of x, the function, is increasing. Okay, it's increasing when you would walk up the hill. It's increasing for values larger than 1. Okay, we can see where's it increasing and where's it decreasing. It's decreasing for values less than 1. Okay, for values less than 1, you'd be walking down the hill. And so that means we can draw the sine diagram of the derivative function from these two bits of information. So if this is the sine diagram of the derivative, we know that it has negative, all right, because we know when f of x is decreasing that the slope is negative. And when f of x is increasing, the slope is positive. And so let's really point out what we've been doing in the past is we've been finding it algebraically, drawing the sine diagram, and we're going from that to this statement. Now we're just doing the opposite. We're looking at this, we're noticing this statement, and then we're drawing the sine diagram. So we're just going in the opposite direction. And now from here, we can draw a graph of this very easily. If I'm going to draw a graph that satisfies this sine diagram, what is a sine diagram but just an indication of when it is above and when it is below the x-axis? And so this function goes like that. Okay, it's at x is 1. It's below the x-axis, and then it is above. This graph generates this sine diagram. This sine diagram will generate this graph in turn. Okay, next it says to graph the second derivative. So for the first derivative, we're looking at when's it increasing and decreasing. For the second derivative, remember we're looking at when is it concave up, when is it concave down. And so we can see this one is concave up for all values of x. There are no points of inflection. So we're going to make that statement, concave up for xer. And what that means then is the sine diagram of the second derivative is just always positive because there are no points of inflection. There's nowhere it changes shape. And so then if we're to draw a graph of this function, it's just the equation of a horizontal line. It doesn't depend on the value of x. So let's provide some further justification for that. Firstly, here we should look at that and we should recognize that's a quadratic, okay, so it's of the form ax squared, okay, it's some type of quadratic. And when we differentiate it, we get 2ax, which is the equation of a line. We don't know what the y-intercept is, that's not relevant. What we're interested in is when is it below the x-axis and when is it above. And that's the point where it passes. And then if we differentiate 2ax, we're just going to get 2a, which is a positive number. We know it's positive because the quadratic's opening upwards, which means a is positive. So 2a is just going to be the equation of a line. Right? F dash of x equals 2a, a horizontal line. Okay, let's move on to the next one, and let's repeat the same process. So probably at first we're going, I'm not really making some connections here. Maybe I can just point out as well, this table here, this is the golden table, and that's really summarizing those connections between the two. So it's telling us what each function tells us in relation to 0. Okay, here I've said we want to make note, when is it increasing, when is it decreasing? So if we look at this function, we're not given these points, but we can safely assume that they're halfway between -2 and 0. So that would be x is -1, and this is +1. Notice how I'm not concerned with the y values. I'm just worried about the x values. And so we can see it's increasing, all right, where are we walking uphill? Okay, it's increasing for x is less than -1, and it would be increasing for x is larger than 1. And then it's decreasing in between those two. Alright, so that's how I'm getting that. Increasing, decreasing, increasing. I'm just making note of it from looking at it. And now I'm going to draw that sine diagram of the first derivative. Okay, the roots are -1 and 1. And I know if it's increasing, if the function's increasing, we have positive slope. And if it's decreasing, we have negative slope. And so now we draw a graph of the first derivative. Okay. It's above the x-axis before -1. Between -1 and 1 is below the x-axis, and after +1 it is above the x-axis. Okay, second derivative, we're going to consider, all right, we always look at the original function. When is it concave up? When is it concave down? What we can see from looking at it, concave down until we get to here. That's where the point of inflection is. So it's concave down before 0 and then concave up after 0. So we'll make that statement. Concave down for x is less than 0. Concave up for x is larger than 0. And so the second derivative, the root on the sine diagram is going to be 0, because that's where the point of inflection occurs. All right, remember, points of inflection on f of x are roots on the second derivative. And because it's concave down, that means it's negative for values less than 0. And because it's concave up, positive for values larger than 0. Okay, so when we're doing 3D.1, what we're doing is we're looking at the sine diagram of the second derivative, and we're going, when is it negative? Oh, it's concave down. When is it positive? Oh, it's concave up. Now we're doing the opposite. We're looking at the original function. Here it's concave down, so that means it has to be negative. Here it's concave up, so it means it has to be positive. And now we're ready to draw a graph of that. Okay, that's again going to be the equation of a line. It goes from below to above, and it crosses at 0. Okay, let's point out a few connections here. Firstly, turning points, so that is local max and local min. Turning points on f of x are always roots on f dash of x. Okay, look, local max at -1, root at -1. Local min at +1, root at +1. Okay, so turning points on f of x become turning points become roots. Okay, the last connection to make is that there's a point of inflection here. Okay, so point of inflection on f of x becomes stationary point on f dash of x. Okay, so that's articulated clearly in the last row of the table. Point of inflection, stationary point. And then we know stationary points become roots. Look here, stationary point becomes a root. All right, so even if you're just to consider this function, we can use this one to inform us, Nick, about this one. All right, look, decreasing until we get to 0. Decreasing until we get to 0. Increasing after 0. Increasing after 0. Okay, so we can generate this graph from here. and we can generate this graph from here. It's going to satisfy both of them. Okay, any questions? Okay, move on to C. Now in C, we're not told very clearly these points, so we're just going to describe them ourselves. We're going to say that that turning point occurs at x is 1, and a point of inflection very clearly here in halfway between them at x is 2. Okay, concave down, and then changes to concave up. Alright, so now, as you get good at these, okay, it's not necessary to make these statements. It's not even necessary to draw the sine diagram. Okay, you're just getting marked on drawing the graph, but I find the sine diagram really helps me. Okay, so what we're going to do is we're going to draw the sine diagram. So we're not going to make the statements, we're just going to jump straight to the sine diagram. And so what I can see are the turning points. X is 1 and x is 3. They're where the turning points occur. And I can see that it's increasing until we get to 1, and then it's decreasing between 1 and 3, and then it's increasing after 3. So I've generated the sine diagram of the derivative just by looking at the original function. Now we can graph that. Above, below, and then above. Now, again, I've said we're not interested in the y values so much. The only thing you really need to get right is the roots and the y-axis, okay? I had someone like drawing these before, and they were putting the y-axis there. That's not where the y-axis is, okay? So make sure we've got the roots in relation to the y-axis. Excellent. Let's go for the second derivative. So for the second derivative, we want to know when is it concave up, when is it concave down. And so we're looking at it, we're going, there is one point of inflection. There's no others. And the point of inflection occurs at 2. And what we can see is it's concave down before 2, so it's negative. And then it's concave up after 2, so it's positive. And this is the equation of a line that goes from below to above. Okay. Let's re-emphasize those connections. So firstly, a good way to think about this is that this is a cubic. Okay, we have a single root here and a double root here. So this is a cubic. Okay, when you differentiate a cubic, you get a quadratic, and when you differentiate a quadratic, you get the equation of a line. Okay, so we can see that happen there. We've said turning points on f of x become roots on f dash of x. Okay, so we can see that clearly. The turning points, the local max and the local min, become roots. And the point of inflection, points of inflection on f of x become stationary points on f dash of x. Look, there it is, and there it is, stationary point. The slope is horizontal. Okay, and then we can make that connection again. Oh, stationary points on f of x, that's at x is 2, become roots. Okay, and again, this function decreasing till we get to 2, decreasing till we get to 2, increasing after 2. Alright, so they should all connect to one another. Let's move on to D. Alright, so we're decreasing till we get to 0. Increasing till we get to 2, decreasing till we get to 3, I suppose, and then increasing after 3. So, on the sine diagram, we've got 0, 2, 3. Decreasing, increasing, decreasing, increasing. Okay, so then if we're going to graph that, so we've got 0, 2, and 3. So it's below the x-axis till we get to 0, and then it's above between 0 and 2, and then it's below between 2 and 3, and then it's above after 3. So that's how we're generating that. Okay. Stationary points. So we've got 3 of them. They become the roots. Next, let's go for the second derivative. Okay, so the easiest way is just to look, when are the points of inflection? We have one here. Alright, somewhere between 0 and 2. Let's say that's at x is 1. And then we have another one here somewhere. We'll say at 2.5. Alright, so concave up until we get to there, then it's concave down, and then it changes back to concave up. So our roots, 1 and 2.5. Okay, when it's concave up, the second derivative is positive. When it's concave down, the second derivative is negative. When it's concave up, it's positive. And we'll sketch the graph of that. Above, below, above. Okay, so we've said turning points. Okay, again, so we can generate this graph just from looking at the original. That's my inclination, that's what I like to do. But we can confirm it by looking at this one. What you can see, it's increasing until we get to 1. Increasing until we get to 1. It's decreasing between 1 and 2.5. That's going to be there. And then increasing after 2.5. The other thing, points of inflection here, they're the turning points. See how that's a turning point? That's a turning point. That point of inflection comes here. And turning points here are roots on this one. Okay, on to question 2. Anyone still on this board here? Alright, we'll rub it out. So question 2 is a little bit different. Sketch it, seems to me. Okay. Here we have to read, you have to read very carefully. Okay, you also have to be very precise. What's the graph here? And it tells us this is the graph of f dash of x. This is the graph of the first derivative. And it says, draw a graph of f of x. Draw the original function, draw a possible graph, because there's actually lots of solutions to this. Draw a possible graph. And so what we should do, we should just look at this and go, this is the slope function. And if we were using our calculator, right, we just use our slope function to draw the sine diagram. It's going to be positive, then it's negative till we get to 1, and then it's negative again. Okay? That sine diagram is just a sine diagram of this function. This is the sine diagram of the derivative. And so what that means, our original function, now we have to think about it in terms of the original function. This is where it's a little bit different. We're not just differentiating, we're going back the other way. And we're using this to tell us what's going on in the original function. Well, we have a local max. We can see it's increasing until we get to -3 and then decreasing. We have a local max at -3. And we have a, what's going on there? Stationary point of inflection. Decreases, goes horizontal, keeps decreasing at +1. Alright, so we'll try and demonstrate those. So local max, there we go, at -3, and then it's decreasing, goes horizontal, and then keeps decreasing. Okay, and that would illustrate that one. And the reason there's lots of possible solutions is because we're not told its relationship with regard to the x-axis. So it could be completely below, completely above. Doesn't matter as long as we have it shaped approximately right. What are we looking for? Local max, stationary inflection. Okay, how do I know it's stationary inflection? Because the sine diagram has this property, negative, negative. Alright? So we're using f dash of x to inform us about f of x. Okay, and again, like now we're going the opposite way to what we were doing before, but you can see turning points on f of x are roots on f dash of x. Turning points are roots. There's a turning point, root. Okay, move on to the next one. We'll just leap straight to the sine diagram of this one. -2 and +4. It's below, above, and below. That's the sine diagram of the first derivative. And so what this means is on the original function, we have a local min at -2 and a local max at +4. And so we can just illustrate that something. Local min here, local max there. That's at -2, +4. Again, we're not told its relationship with the x-axis, so we're only interested in its shape and those things occurring at that specific point on the x-axis. Okay, so maybe you've noticed, but we've actually just done all of the questions for 3D.2 together that are in the textbook. So I've created some more. That's these 4. What I would like us to do first is these 4 questions. And then if you want, you can start to make your way through this booklet, which is questions like this, but they're picked from old exams. So this is, again, like the conjecture problem, like the first principles problems, this is a common thing that they ask. They ask it like 50% of the time. And they're quite creative. It's about really understanding all of those connections between the 3 functions that we deal with. So you've got 2 options. Definitely do the first 4 here, and then if you like, you can proceed with this booklet, or you can go back and do some more of 3D.1. But everything of 3D.2 we did just now, so you don't need to have a look at that exercise anymore.